The wave. It's the simplest gesture out there. We use it to greet people, say goodbye, and show our frustration. We see people waving all the time. And even to the physicist, waves are pretty useful and omnipresent. Bouncing on a trampoline, that's a wave. Jerking a rope up and down, that's a wave. Throwing pebbles in the water, that's a wave. Listening to me saying this, that's a wave. Yes, sound is indeed a wave. So let's look at waves as a physicist would, shall we? A wave is a disturbance traveling through space.
Hi, don't disturb me.
Waves carry energy and they travel through a medium. Here's a rope. I fix one end of it to a point and jerk the other end up and then back down to its initial position. What I've created here is a pulse, a disturbance. The pulse originated from the left, where I jerked the rope, and propagated away from the source through the rest of the rope. It traveled as what we called a wave. And since it was a single pulse, we call this a pulse wave. If I were to continually go up, down, up, down, up, down, what we'd get is not a single pulse, but a full-on wave, a continuous wave. This wave looks a lot like the graph of y equals sine x, right? This continuous wave has several properties that define how it looks. It has an amplitude, wavelength, period, frequency, crest, and trough. The crests are the bumps on the top, and the troughs are the bumps on the bottom. The distance of the crests and troughs from the resting position, or middle of the wave, is the amplitude, and the distance between two consecutive crests or troughs is the wavelength. It's the distance covered by the wave in a full cycle. Now, this wave is traveling through the rope. As time elapses, the wave travels further and further away from the source. And you can see how each crest and each trough is covering distance with time. And similar to how we calculate the speed of a moving bicycle by dividing distance by time, here the speed is calculated through multiplying the wavelength by something called the frequency. The frequency is essentially the number of full cycles, wavelengths per second, and it's measured in hertz. The frequency is inversely proportional to the wavelength. This wave has a wavelength of 1 meter and a frequency of 1 hertz. Hence, the speed is 1 meter per second. There's also a property called the period, which is the opposite of frequency. While the frequency is the number of cycles per second, the period is the number of seconds it takes for one full cycle. Speed is equal to the wavelength times frequency. Say we increase the frequency of the wave. The result will be a decrease in the wavelength. And if we decrease the frequency, the wavelength increases. And all throughout, the speed of the wave remains constant. The speed of the wave does not depend on the properties of the wave. It is completely independent of the amplitude, the frequency, period, wavelength, etc. The speed of the wave is only dependent on the medium in which it is traveling. The medium is the thing through which the wave propagates. In this case, the wave is propagating through the rope. If we alter the rope itself by stretching it out and stiffening it, the wave speed will then change. In this situation, the wave is propagating horizontally. The crests move out eastward, but the actual particles in the rope, in the medium, are moving northward and southward. The rope is not moving anywhere. It's still stuck in the same place. The particles in the rope are jiggling all around. They are moving vertically. The waves themselves travel horizontally, and the bumps, the oscillations of the wave, are perpendicular to that. This phenomenon is called a transverse wave. But what if the bumps weren't vertical? What if the particles in the medium oscillate in the same direction as the wave propagation? Well, in that case, we wouldn't be dealing with a transverse wave. We'd be dealing with a longitudinal wave. If I say, "Hi," I'm making a sound with my mouth. And this sound is a longitudinal wave. The medium it's traveling through is the air, and the jiggling happens with the air particles. When I spoke, the particles next to my mouth moved outward. They were pushed. and bumped into the particles eastward. Those particles then themselves bumped into the next particles, and so on. This sideways motion of air particles gives rise to compressions and rarefactions. Compressions are regions of high pressure, where there are a lot of particles bunched together. Rarefactions are regions of low pressure, where there are a few particles bunched together. This wave may travel outward and hit a surface. When it does so, it will bounce backward and travel in the opposite direction. This is called deflection. When sound waves have a greater frequency, when air jiggles back and forth more times per second, it has a higher pitch. Conversely, when the jiggling occurs less times per second, the sound has a lower pitch. Yes, frequency is a thing in longitudinal waves too. We humans hear sound waves that have a frequency between 20 Hz and 20,000 Hz. The jiggling particles hit our eardrums, and our brains perceive that collision as what we call sound. Beyond 20 and 20,000 Hz, we cannot hear anything. The pitch is just too low or too high. Yes, sound is just a wave. When my physics teacher first told me this, I fell into an existential crisis. I mean, Beethoven just spent his entire life jiggling air? Yes, all genres of music, or music, are just waves. All waves, regardless of what kind they are just disturbances traveling through a medium, carrying energy. Remember how the speed of the wave on the rope depended only on the medium and not the wave properties? Well, that applies here too. The medium here is a gas, air. But we can also produce sounds in liquids, like water, and in solids. And it's faster in both than it is in air. In outer space, however, we cannot produce any sounds whatsoever, because, well, there's just no medium for it to travel in. It's all vacuum out there. It can be laborious to draw compressions and rarefactions repeatedly when studying sound waves. So we often represent these longitudinal waves as transverse waves, just for simplicity. Here, compressions correspond to peaks and rarefactions to troughs. But that's not the only oversimplification we can make of sound waves. You see, sound is complicated. Suppose we have two sound waves moving through a patch of air. To model these two sound waves at once would be very difficult, as we'd have to simultaneously keep track of the displacements of the jiggling particles and their ultramicroscopic interactions with one another. It would take forever for one to do so much. So instead of doing that, what we do is treat both the waves as individual sound particles traveling through the patch of air. These particles, of course, aren't real. They're just oversimplifications of our system, but they make the mathematics far easier than before, and they work in describing the system. These sound particles are called quasi-particles. Now, instead of two sound waves or sound particles, let's suppose you create two identical pulse waves on this rope that propagate from opposite ends. When they meet, and they will meet, they will combine to form a single wave with an amplitude that is equal to the sum of the amplitudes of the constituent waves. This phenomenon is called constructive interference. If one of the waves was on the opposite side of the resting position, we would observe destructive interference when the two would meet. The sum of the amplitudes of these two waves would be zero. Hence, they would cancel one another out. This ability of waves to combine with one another is called superposition, and it works for all kinds of waves: transverse, longitudinal, pulse, and continuous waves. Superposition is also, by far, the coolest word in the physics lexicon. But superposition is not the coolest property of waves. No way. The coolest property by far is diffraction. Say we have a water wave. This is a schematic of how it would look from an upward view. Each line here corresponds to a peak or a crest, and each gap to a trough. Each line can also be called a wave front. Looking at this wave from a sideways angle, we'd see this. Now, Let's suppose that we place an obstacle ahead of this traveling wave. This obstacle has a slit in it, called an aperture, through which the wave can move. How will the wave move? Good question. Will it be like this, or like this? The answer is B. The wave will bend as it passes through the slit, and the pronunciation of this bending will depend heavily on the size of the aperture. If the size of the aperture is made greater, the wave bends less, and if it is made smaller, it bends more. This is what we call diffraction, the bending of a wave as it passes through a slit or around an object. Diffraction is a mysterious property. Why does it occur? Why do waves bend? Well, one geometric model that attempts to predict why diffraction is a thing was proposed by a Dutch physicist named Christian Huygens. It's called Huygens' wavelets. According to Huygens, every point on this wave behaves as the source of the wave. Yes, sounds very weird indeed. From every point on this wave, not just the 5 shown here, a tiny circular wave is propagating in every direction. Remember, every line in this schematic represents a peak, and every gap represents a trough. We don't actually see any of these circular waves themselves, though. 2 circular waves are interfering. Their peaks are interfering, and what we get is a larger peak. If we add more circular waves, which we ought to, we can slowly see that there is a line that forms, a clear line. It's an entire gigantic crest of the wave, and we can see this crest in real life. That's formed due to the constructive interference. This is the model that Huygens proposed to demonstrate how waves move and diffraction. Let's bring in our slit again. When the wave passes through the aperture, we see that a chunk of it at either end is absorbed by the material of the slit. Then, of what is left, we see that the miniature circular wave sources interact like this. There's the usual line at the front, but then at the ends, there is no interference occurring because there's no wave for there to be sources. And so the circular waves just keep on going. They aren't being cancelled out by anything. And so the final shape of the wave that we see is this. That's what we see in diffraction. Huygens' model works, but it's filled with loopholes. Firstly, shouldn't there be a giant peak and wavefront forming at the back of the wave here as well? Well, yes, that is also one thing that the model predicts, and this prediction, of course, does not agree with empirical data. So, what did we do about it? Well, we don't have to do anything, because a guy named Augustin Jean Fresnel already gave us a modification of the model. He said that although each point of the wavefront emits circular waves, the circular waves are not the same in each direction. On the front, they have a high amplitude, and on the back, they have an infinitesimal, a negligible amplitude. And hence, we do not observe any interference or backward traveling waves. This idea is called the Obliquity Factor, and the combined contributions of Fresnel and Huygens in trying to explain why diffraction is a thing is called the Huygens-Fresnel principle. But doesn't this modification seem hasty or lazy and unsatisfying? Well, it kinda does. Think about it. Think about it in your core. Feel it. It feels immoral and lazy, doesn't it? You just come in and say the amplitudes are different at different points of the wave? Just think about it. This guy was evil. I feel evil. You are evil. We are all evil devils. This is not good. Come, let us lead ourselves to a better state of mind. Let us find the light, because finding the light is the key to benevolence and peace. Light is also a wave, by the way. Hi, thank you for watching this video. If you feel certain explanations weren't understandable, or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I've also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.